In this video, we'll see how to design synchronous counter using the second type of flip-flop, that is D flip-flop. Here is the excitation table for the D flip-flop. It has only three columns: present state, next state, and only one input, that is D. Okay. So if you have two inputs, present and next, you have four combinations. And how do we write the output? Whatever is your next state, the D value is going to be the same as your next state. It is 0, 0, 1, 1, 0, 0, 1, 1. Okay. So Q plus and D are same. This is how you can remember the D flip-flop excitation table. Okay. So now we'll try to design the counter for this sequence that is given here. First step, as we have seen in the previous problem, identify the number of bits required for this counter. So what is the highest value in this sequence? The highest value is 12, right? So for 12, how to write in binary? It is 1, 1, 0, 0, which means how many bits are used here? 4 bits. So we have 4 flip-flops in our circuit. So your table will now have 4 present states: QA, QB, QC, QD, and 4 next states: QA plus, QB plus, QC plus, and QD plus. And according to the excitation table for D flip-flop, present state, next state is done, and what else you need? Data value, that is D. Since you have 4 flip-flops, you'll have 4 D values: DA, DB, DC, and DD. Okay. So 4 bits means number of combinations will be 2 power 4, that is 16 combinations. So in the present state, you mention all the 16 combinations in proper order. Just like how we have done for 8 combinations. No, this is now 16 combinations. 1, 0, 1, 0, 0, 0, 1, 0, 1, 6, 7, then comes 8, 9, 10, 11, 12, 13, 14, and 15. Okay. Now to write the next state, look at the given question. So when the input is 0, do you have 0 in the given question? Yes. If it is 0, where should it go to the next value? That is 1. If input is 0, go to 1. Okay. If input is 1, you have 1 here, go to 3. If input is 2, you don't have 2 in the given question. So if that number is not there, put X. If input is 3, you have 3. After 3, it should go to 5. If input is 4, 4 is not there in the question. So X. If input is 5, 5 is there in the question. After 5, the number is 7. If it is 5, go to 7. If it is 6, that number is not there. So X. If it is 7, you have to go to 10. 1, 0, 1, 0. If it is 9, there is no 9 in the given question. Sorry, there is no 8 in the given question, and there is no 9 also in the question. 10 is there. After 10, you are supposed to go to 12. 12 is 1, 1, 0, 0. 11 is not there in the question. 12 is there, but after 12, you are going back to the initial value 0. 13, 14, 15 are not there in the question. Okay. So I hope you have understood now how to write this table. It is very clear now. So now coming to the output D value. What is the D value equal to? It is exactly same as your next state value. Okay, just copy the same next state column to the D column. So DA will be same as QA plus. Whatever is there in QA plus, you copy it and write it in the DA table. DA X, then you have 0, X, 0, X, 1, X, X, 1, X, 0, X, X, and X. Next, DB will be same as QB plus, okay? X, 1, X, 1, X, 0, X, X, 1. DC is same as QC plus. hmm, X, X, and DD will be same as QD plus. 1, X1, X1, x0, x, x0, x, 0, x, x, x. Okay, so your table is complete. Next step will be to draw the K-map and simplify. But remember, now you have 4 bits, right? QB, QC, QA, QB, QC, QD. So you have to draw 4 variable K-map. You have 4 outputs, so you will have to draw 4 variable K-maps and simplify. Find out the equation for dA, dB, dC and dD. Here you have QA and QB. This side will be QC, QD. 0, 1, 1, 1, 1, 0. Similarly, 0, 0, 0, 1, 1, 1, 1, 0. This will be QC bar, QD bar, QC bar, QD, QC, QD, QC, QD bar, QA bar, QB bar, QA bar, QB, QA, QB, QA, QB. Now we have to put these values in the table. 0, 1. For 2 you have x. 3 is not there. For 4 you have x. Where is not there? 6 is x and 7 is 1. Okay. 8, 9, x. 10 is 1. 11 is x. 12 is not there. 13, 14, 15 are x. Okay. So now how to group them? For this, to cover this one, you have options. Either you can take this quad or you can take this quad. Okay, both are correct. Or you can also take this as a quad. You have 3 different ways in which you can group this one. Okay, so let me take this one only. I'll take this as a quad for covering this one, and I'll take this as a quad for covering this one. So 2 groups are done. Your dA equation will be, for the first group, I'll get the answer as QB and then QC plus the second quad is going to be QC, QD bar. You can do like this. You can take QC common and write QB plus QD bar. This reduces the number of gates. For the first equation, you will have to use 1 and 2 AND gates, 2 AND gates and 1 OR gate. But for the second equation, only 1 OR gate and 1 AND gate is enough. Instead of 3, you can draw this circuit using only 2 gates. Okay, this will be your final equation. Similarly, you have to do for dB, 4 variable K-map. You can pause the video and try to simplify it on your own, and then you can verify your answers here. Two and three, 2 and 3, 4 and 5, 4 and 5, 6, 7, 8, 9, 10, 11, 13, 14, 15. So here again, this time let me go with this as the group, and then I can take this as a quad. Okay. Please, when you simplify K-map, always start with the highest number, highest grouping that is possible, bigger group. Okay, don't start with the smaller group. Start with bigger group always. So answer for this will be QA, QB bar, that is this one, plus QB bar, QC. Okay, QB bar, QC. Again, you can take QB bar common, you will get QA plus QC into QB bar. Okay, this is the answer for the second one. Now coming to DC. 0, 1, 2, 1, 2 are there, 4, 5, 6, 7, x1, 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 then xx, 0, 9, 10, 11, 13, 14, 15. So here you have three ones here, this, and this. So you can cover these two ones with the quad here. You can cover this one with the quad here. Okay, so your answer for DC will be QC bar QD, that is this one, plus QA bar QB. Okay, coming to the last one. One, X1. Okay, then X1, X, X1, X0, and XX, 0X, X, X0, X. The last one will be 0, X, X. So you have 1, 1, 1, and this one here. Uh, Now, if I had a X here, I could have made an octet with the first row and the last row, but yeah, that option is not there. You can go with this quad, and you can, to cover this one, you can go with this quad. Okay, so your DD will be, hmm, it will be QA bar, QB bar, plus QB bar, I'm sorry, QC bar, QD. This will be the answer for D, the fourth one. So all you have to do is just draw the circuit for these four equations. So four D flip-flops will be there. And as usual, take all the clock inputs, short it, and give a common clock. Okay. And you have a D flip-flop, so only one input will be there, DD, DC, DB, DA. Output will be QA, QA bar, QB, QB bar, QC, QC bar, QD, QD bar. And if you look at the first equation, dA is QC into QB plus QD bar. Okay, QC into QB plus QD bar. So you need a OR gate first with QB and QD bar, and the output of this is given to AND gate with other input being QC, and this is going as input to DA. Okay, QC into QB plus QD bar. Similarly, for DB, it is QB bar okay, the equation for DB is QB bar into QA plus QC. So first you have to take QA plus QC OR gate. Output of this is given as input to AND gate, and this output goes to DB. OR gate inputs are QA and QC, and for AND gate the other input will be QB bar. Okay, this is the circuit you have for DB. Similarly, the third and the fourth one. Third one, DC, is, so this is your DC. Here you will require two AND gates, one for this, other one for this, then total OR gate. So I'll need two AND gates here. Output of these two will go as input to the OR gate, and that goes as input to DC. So the two inputs for first AND gate will be QC bar and QD. Whereas for the second AND gate, it is QA bar and QB. Okay. Similarly, in the last equation also, we have two AND gates with OR gate. Input for these two will be QA bar, QB bar, QC bar, QD. QA bar, QB bar, QC bar, QD. Okay. So this is your synchronous counter design using D flip-flop. Right? For any given sequence, you can draw the table. Main thing is know the excitation table for individual flip-flop. Same way, you can design counters using JK and T also. You please practice with it. For the same question, you can practice with those flip-flops. And if you have any doubts, you can always get back to me using the comment section. Okay. For JK flip-flop, it is same as your SR. You'll be having two outputs for each flip-flop. JAKA, JBKB, JCKC, JDKD, so on, depending upon how many bits are there. Whereas when it comes to T flip-flop, you'll be having single values for each flip-flop. TA, TB, TC, TD. It is exactly same as your D. Okay. Only one value will be there. One output columns will be there. If it is 3 bits, you will have TA, TB, TC. If it is 4 bits, you will have TA, TB, TC, TD, like that. For JK, you will have JAKA, JBKB, JCKC, JDKD. Okay. So this is how you can design any counter, synchronous counter, using any of the flip-flop, SR flip-flop, JK, D and T. Main thing is each flip-flop, what changes here is the excitation table. So you should know the excitation table of all the four flip-flops. Only with that you'll be able to solve this question, which is of 10 marks. Okay. Otherwise it becomes very difficult for you, right? So that's it about the synchronous counter. Thank you.